Now in today's class, we'll see the concept of normalization. Guys, basically normalization means simply it's a kind of decomposing a single relation into decomposing single relation into multiple relations. I can call it as normalization. Right? What is the necessary to decompose the single relation into multiple relations? Because simply to avoid the redundancy, we can go for decomposing the tables. Am I right? Have you seen any example regarding this? Right? Earlier we have discussed one example called like student number, student name, department number, department name, HOD number, HOD name, and so on. We have seen, right? So as it is a kind of a single table, this table is going to have entire data. Table is going to have entire data. But if you are able to observe, this table can get redundancy. Am I right? Where you are going to get redundancy? If multiple students are belongs to the same department, definitely they are going to get same HOD, same phone number, same department name. So that is where we are going to get the redundancy. So to overcome this, what we did there, we tried to simplify this into small tables. Small tables. This is what generally I can call it as normalization. So normalization simply decomposing a single relation into multiple relations. I can call it as normalization. So the advantage of normalization is we can able to avoid the redundancy by eliminating various kind of insertion anomaly, deletion anomaly, and updation anomalies. Am I right or not? Yes. Once we decompose a relation into multiple relations, automatically these anomalies are going to be eliminated. That is the advantage of normalization. Right? So how can we do this? Right? Basically, with the help of our illusion, we can able to define or we can able to divide the relation into multiple relations. But if the problem is a kind of some kind of real world problem, so basically illusion is a kind of a difficult task. So that's the reason we are going to go for some kind of mathematical thing. So that's the reason we are trying to discuss various kind of normal forms. Among those, one kind of normal form I can call it as first normal form. So normalization means simply a normal form only. Right? So what does the meaning of normal form means? Whatever the things that we are going to create a table, every table will comes under first normal form. Means if you are going to take a single cell, this single cell contains single value or multiple values? Single value. Then this is a kind of general rule. If would like to say that a relation is in one normal form. And also, can we allow any kind of duplicate columns? Duplicate column names can we allow? If I say a column name as department number, can I able to add one more column name as department number? No, it is invalid because it may get confusion which department number I have to consider. So that's the reason we should not allow duplicate column names. What about the rows? Duplicate rows are not there, right? Meaning that rows should be in a queue. Rows should be in a queue. And is there any restrictions on the order of the rows? In any order we can able to write. There is no problem. There is no restriction. Meaning that first row should be having the serial number as 1, second row should be having the serial number as 2, and so on. It is not like that. You can write the first row serial number as student ID 100 and third row student ID as 1 also. There is no problem. Meaning that there is no restriction on the order of rows. Is there any other some kind of other kind of rules we can able to observe with the help of basic knowledge? What about the domain of values? Domain means what? The type of data that is going to be allowed in a particular column, right? See, for example, if I say that serial number domain is of type integer, can we allow other domains? No. That's why domain should be of same values. Domain should be of same, meaning that it has to allow only same integer values or it has to allow only same string values, like that. So these are the some of the rules that we can able to observe when we say that a decompose is in one normal form. One normal form, right? So, and something like which if you say trying to write some kind of columns, those columns should be simple columns. Columns should be simple columns. Am I right or not? So So it should not be kind of a composite columns, or it should not contain a kind of multi-valued columns, right? So always your column should be simple columns. Means if you are able to observe, while converting ER diagram to relational model, whatever the output that we are going to get, by default they are going to be comes under one normal form. There is no particular things you have to follow to get the relation into one normal form. Simply try to follow the rules of conversion from one ER diagram to relational model. By default everything will becomes under one normal form. But the thing here is, if you are able to observe some kind of examples, like if you take this example only. Now, if this particular relation is in 1NF, is this relation is in 1NF or not? Yes, it is in 1NF, because there are no duplicate columns, there are no duplicate rows. At the same time, there is like if you assume the single cell doesn't contain any kind of duplicate values also. So I can say that this particular relation is following a normal form called one normal form, first normal form. But can we say that is redundancy is eradicated here? No. With the help of this example you can understand, right? Because department name, HOD, department number, these are going to be a kind of redundancy. So we can't guarantee that if I am saying that this is in first normal form, 100% redundancy is not avoided, right? Means once we apply the normalization concept, 100% redundancy cannot be directly avoided, but we can able to avoid it through various kind of other normal forms, right? The other normal form is a kind of second normal form. We can say that 2NF, right? This 2NF is also not going to completely eradicate the redundancy. It may eradicate the redundancy up to some extent, right? For example, let me take a simple example. Let me take the column as ABC and assume that the values will be like this. For example, 1 A C1, 2 A C1, 1 B C2, 2 B C2. For example, like if you take the remaining things. Observe now, is it in one normal form? Is the relation is in one normal form? Yes, it is in one normal form, meaning that basically it is following all the rules which was given in the one normal form. But is it avoided the redundancy? No. If you are able to clearly observe, we can observe that this is a kind of redundancy, meaning that for the same A, the C1 is there, for the same B, C2 is there, for the same C, C3 is there. So can we able to write some kind of functional dependencies for this? Yes or no? Can I say that B determines C? Yes or no? Meaning that if I am going to give the value of B, I can able to get the value of C or not? Always. Can I write in another way? Can I take the combination of AB? Can I get the value of C? Yes or no? Obviously, independent value is generating a unique value. Combination also generating the unique value. There is no problem in that, right? So, if we can able to write like this, right? So, how can we reduce the redundancy here? So, basically, with our illusion, we can redundancy. We can avoid redundancy. How? Can we write the one table called BC? Can I write the another table? What is the table? A, and another one is B. If I write like this, so here in the relation R1, number of columns may not be reduced. It may be as like as the actual table, like R. But if you take the relation R2, is it going to reduce the number of rows or not? Yes, something like A C1, B C2, and C C3, and it may have many values here also, right? Now this is the way you can able to reduce the redundancy, right? So as it is a kind of simple illusion, simple example, we can able to directly write. But coming to the real world example, it is very difficult to write like that, right? So that's the reason we come across some kind of formulas, right? So the thing is, when we are saying that a table is in 2NF, now is it in 2NF or not? Yes, it is in 2NF. Assume that, right? So when we say that it is in 2NF means it has to compulsory follow 1NF properties and it has to avoid partial functional dependency. This is the definition of 2NF. 2NF means it should be follow the principles of 1NF and it should be free from partial functional dependencies. What is the meaning of partial functional dependencies? Right? You may get question. So basically partial FDs means this example clearly defined. If I say that this is a point of functional dependency, AB determines C, right? Is AB is itself is going to determine the C. A part of this is determining again the same thing. Am I right or not? This kind of situation I can call it as partial functional dependency. Meaning that if I say X determines Y is a kind of a partial functional dependency, and if you observe that X is a kind of a candidate key. Where this candidate key contains a combination of various kind of attributes like x1 union x2, right? Now if x1 able to determine y or some other thing, I can say that this is a partial functional dependency, right? So means if you say that x is a candidate key, it contains various kind of attributes, right? Each and every attribute I can call it as a prime attribute. I hope you remember this word. Prime attribute means a part of the candidate key. Every attribute I can call it as a prime attribute, right? So simple thing is partial functional dependency means prime attribute should not determine any other thing. Then I can call it as partial functional dependency. So to make it clear, I will modify the definition. If prime attribute can determine anything, I can call it as a partial functional dependency. Is it okay, everyone? For example, simply let us take example AB determines C. Assume that AB is a candidate key. Candidate key is a AB. Now there is one more functional dependency called B determines C. Now I can say that this is a partial functional dependency. Why? A is a prime attribute, B is a prime attribute. One of the prime attribute is determining something new. So I can call this B determines C is a partial functional dependency. Right? Now you can able to observe here. Right? What is the need of avoiding this partial functional dependencies means if I are able to observe is AB determines C is okay. A part of it also determining something because B is a prime attribute. So at that situation, you may get certain kind of redundancy data. That's the reason they formulated this rule, right? So in simple conclusion, if I say that it is in a 2NF, you have to avoid partial functional dependencies. Right? So for example, let me try to solve this one. You can get like clear idea. Let me take the relation R of A, B, C, D and a set of functional dependencies are AB determines C, B determines D and they have given the candidate key as assume as AB. Assume as AB. Now can we say that is it in 2NF? Try to observe. First tell me is it in 1NF? Yes, by default everything is in 1NF. Now if I say that it is in 1NF, we have to identify whether it is in 2NF or not. Is it in 2NF? If you would like to identify whether it is in 2NF or not, you have to check for first partial functional dependency exists or not. If partial functional dependency exists, I can say that it is in not in 2NF. If not exist, I can say that it is in 2NF. I can say it in 2NF, right? Now, how can we check whether it is in partial functional dependency or not? You have to first identify what you mean by candidate key, right? What is the candidate key here? AB. What is the meaning of partial functional dependency? First, you have to identify various kind of prime attributes. What are the prime attributes? Prime attributes are A, B. If these independently can able to determine some other thing, I can say that definitely there exists a partial functional dependency, right? Now with this example here, is there any partial functional dependency is there? Yes, right? AB is a candidate key. A part of it is one B. B is determining something which may not be the same for all. B determines something, so I can call this as a partial functional dependency. Partial functional dependency, right? Now I can say that it is in not in 2NF. It is not in 2NF, right? So when it is not in 2NF, you have to convert it into 2NF. Why you need to convert it into 2NF? To avoid some redundancy. To avoid some redundancy, right? So what you can do now? Once you identify the primary attribute, and if you observe any kind of partial functional dependencies, try to find out the closure for that. Try to find out the closure for that. What is the closure of B? B and B. So this will be the one relation. I can call it as R1. Call it as R1. Meaning that if I say that R1 is one relation, this relation I am trying to decompose into multiple relations. Among those one relation is R1. Is there any other partial functional dependencies are there? No. No, right? So that's the thing. The remaining things will become under another relation called R2. What might be the attributes of the another relation? C is compulsory. A is compulsory. Very good. That's it. Try to observe. If I say that R2 is AC, R1 is BD, is it the correct decomposition? No. Once we decompose, we have to apply various kind of other properties also, like lossless join, dependency preserving, all those things, right? Once we apply here, lossless join property, is it lossy decomposition, right? Lossy decomposition. Why it is lossy decomposition? Because there is no kind of common column. So you have to make sure that once we decompose the relation to multiple relations, you have to combine them again. So for that, what you have to do? You have to put one common column. What is that common column? Can I include here B? Why I am going to include B here? Because B is a candidate key for another relation. B is a candidate key for another relation. So I can say that R2 as ACB. Now can we say that this is in 2NF? Obviously it is in 2NF. This is the way you can able to define, or you can able to reduce the redundancy. Okay, now. So to get more clarity, take out one more example. The relation, let me take, the relation contains A, B, C, D, E, F, G, H, I, J. The relation, and they have given various kind of FDs are AB determines C, A determines D, B determines F, F determines GH, D determines IJ. These are the FDs possible, and if they haven't given any kind of candidate key, we have to find out the candidate key also, right? What might be the candidate key here? Can we expect this solution? This question we have taken earlier already, right? We have to. So what is the simple solution to find out the candidate keys? We have to start with the single level attribute, 2 level, 3 level, and so on. But much more simple is we have to find out the necessary attributes. Necessary attributes means what? Which are not there in the right side, right? So what might be the not there in the right side? A is not there in the right side, B is not there in the right side, and C, D, E, and all the remaining things are there in the right side. So minimum, if I say that a candidate key, it should have a attributes as A and B. So first we'll try it with the AB closure. Try it with the AB closure. What is AB closure? Basically AB you will get, trivial you will get, from AB you will get C, from A you will get DE, from D you can get IJ, from F you can get, B you can get F, from F you can get GH, from D you can get IJ. Means you are getting all. So I can say that candidate key is AB. Once we identify the candidate key is AB, what might be the prime attributes? A part of a candidate key, everything will becomes under prime attributes only, right? Now the question is it in 1NF or not? First, obviously it is in 1NF. Now we have to check whether it is in 2NF or not. So to check whether it is in 2NF or not, you have to identify various kind of partial functional dependencies. Partial functional dependencies means prime attribute should not determine anything. right? I'm making some kind of explanation, right? Prime attribute can able to determine some other thing. I can call it as partial functional dependence, right? If you are able to observe, A is a prime attribute which is determining something, so I can say that this is a kind of partial functional dependency. Similarly, B is a determining something, I can call it as partial functional dependency. Any other things are there? No. So I can say that once we observe at least one partial functional dependency, I can say that the relation is not in 2n. What is the maximum normal form it is following? 1nf. Very good. So like this, your questions may be get in the competitive examination, which is very, very important. Okay, fine. Now we need to convert it into 2nf. So for that, the simple solution is you have to take out one more partial functional dependency. I have to find out the closure. What is A closure? So I am trying to take out this one. A closure is A you will get, D you will get, E you will get. From D you can get Ij. You can get Ij. So I can say that this is one relation R1. One relation R1, right? So if I are able to observe, so I will give some simple clue here. So try to write out all the attributes of A, B, C, D, E, F, G, H, I, J. Now in this particular relation R1, what is the candidate key? A. A is the candidate key. What might be the remaining attributes? D, E, I, J. All you can just cross check. Okay. Now what might be the another partial functional dependency? B closure. B, F. From F you can get G, H. Inner things are possible? No. So here the candidate key is what? B. So this is the relation R2. So you can just write the F, G, H. Right? So now you will get the idea why I am cancelling those. Now you have to take one more relation called R3, which will be useful for to combine all the relations to get the property of lossless join property. Am I right or not? So now what might be the R3 contains? All the remaining things. All the remaining things which are not crossed. Right? So R3 contains A, B, C. So now this relation is in 2n. Okay, na? Right? So if you are able to observe, you can write various kind of FDs possible here, and you can just cross check. There won't get any kind of partial functional dependency. As at the end of the relations, as you are not getting any kind of partial functional dependencies, I can say that the relation is in 2n.